Hello everyone, my name is Yifan Li, a PhD student from University of Bristol. My research is about lattice fatigue. Today I will introduce you guys the fatigue properties of triangular lattice plates. First of all, I will give you some introduction about the lattice materials. Cellular structures are prevalent in biologic systems and man-made engineering structures, for example the wood and bone. Lattice structures are a subset of cellular materials in which the microstructure is regular and periodic. The unit cell structure repetitively composes structures by different kinds of topologies and can constitute different ranges of geometries. Lattice structures can be defined as 2D lattice and 3D structures depend on their expansion of dimensions. 2D triangular lattice, which has a unit cell with 6 node connectivities, is a good representative of stretching-dominated lattices. These materials are utilized in many engineering applications, such as lightweight support in aerospace industries. The objectives of this research understanding the mechanisms of fatigue in lattice structures and proposing a method to predict fatigue life of triangular lattice plates, then obtain the crack propagation rate by using continuum mechanics. We will extend the proposed method to 3D lattice in the future. In the lattice plate, crack will first initiate in a single strut when it's under cyclic loading. Then the microcrack propagates to the critical length of fast fracture. At the same time, the strut breaks and the macrocrack can be seen as advancing by unit cell. The macrocrack tip is assumed to be at the center of the cell, rather than at the unbroken struts that adjacent the crack. The macrocrack length in this research defined as the horizontal length of the whole crack. In triangular lattice plates, the stress state involves predominantly stretching in struts, and the bending stress is only a few percent of the axial stress and the failure sites. We assume that the few percent bending stress has less effect on strut fatigue life. The struts within the plates have identical behavior as the single struts in tensile fatigue tests. Individual struts in triangular lattices can be simplified as a normal force applied in the axial direction of strut cross-section. Because triangular lattice is stretching-dominated structure, load life curve is usually used to study the fatigue properties of structure. The fatigue life of individual struts can be summarized as dependent on the amplitude of the cross-section force. At the same time, the cyclic loads will also accumulate damage in struts that are not adjacent to the crack tip, and this phenomenon can be described by Miner's rule. First, we will do fatigue tests of single struts cut from the lattice plates and obtain the load life curve. Then the load life curve will be used in lattice plate fatigue to predict the fatigue life of individual struts. The numbers of the cycles for individual struts to fail are summed to calculate the specimen life. At the same time, damage accumulation in individual struts will be considered by Miner's rule. Water jet cutting was chosen to manufacture the lattice plates because this method will guarantee the temperature of material not increase during the manufacture procedure, which will decrease the strut's distortion. The compressive residual stresses introduced during the manufacture processes can also improve the fatigue performance. All the plates were cut from 2 mm thick aluminum alloy 1058 sheet. The designed strut length and thickness are 10 mm and 1 mm. At least 24 unit cells are present in all directions to avoid the boundary effect in lattice structures, which can also ensure sufficient fatigue crank propagation paths. An experiment was conducted on sheet-type specimens designed according to the ASTM E8 standard to obtain the mechanical property of aluminum alloys. An Angstrom hydraulic testing machine with 5 kN load cell was used for the tensile test on a displacement-based control with 0.25 mm per minute velocity. The yield stress and ultimate tensile strengths were measured, and the elastic modulus and Poisson's ratio are also obtained. Angstrom machine with maximum load capacity 1 kN sensor was used in single strut fatigue test. The loading frequency is 10 Hz, and the load ratio R is equal to 0.1 for all tests. All fatigue tests were force controlled to avoid specimen buckling. The load life curve of fatigue lattice single struts was constructed by testing at least 2 struts and 1 identical load amplitude. A single strut with 5 loads was cut from lattice specimen and glued with small aluminum plates to be clamped by test machine grips. Figure 7 presents the load life curve for single struts. It will be used to predict fatigue life of individual struts in lattice plate. 6 identical triangular lattice plates divided into 3 groups are gained to test the fatigue life, and 3 lengths of edge initial crack were introduced into the plates. The crack was cut through 2, 4, and 6 cells in the plates respectively, and the maximum loads of the 3 groups lattice specimens are 3000 Newton, 2700 Newton, and 2400 Newton. Test conditions are the same as the single struts, except that the testing machine will use a maximum load capacity 10 kN sensor. The test machine will be stopped when one strut near the crack tip break to record the cycles, then start the machine again to run the test. The whole fatigue life of plates is the addition of the fatigue life of different individual struts in lattice plate. The fatigue crack paths in lattice plates have a specific pattern in all 3 groups. The crack will develop in direction 30 degrees to the horizontal axis of introduced edge crack in the upper half of lattice plate. The crack path is also similar as monotonic fracture tests of triangular lattice plate in literature. The fatigue failure of triangular lattice can be described into 3-stage mechanism. In the first stage, the crack length propagates very slowly for a long time. In the second stage, the crack length has a small increase after a certain number of cycles, while in the last stage, the struts break instantly and causes the crack growth very quickly. Beam model was used in the FEM to simulate the individual struts in lattice plates, and the maximum tensile load of individual struts near the crack tip was obtained from the FE results. In the 2D beam model, each strut is meshed by B21 elements with 1 mm seed size. The strut length and thickness in the model were 10 mm and 1.1 mm based on the measured data. Material properties in the model are from the Unixel tests. In FE simulation, the struts with largest tensile load will be deleted to extend the fatigue crack paths. Simulating crack paths in all lattice plates are the same as fatigue experiments. The fatigue crack propagates along 30-degree direction to the horizontal axis. The comparison of predicted fatigue life by proposed method and experimental results are shown in Figure 11, and the predicted results agree very well with the experimental results. In order to verify the validity of the proposed method, the comparison between experimental fatigue lives of individual struts in lattice plates and the predictions is shown in Figure 12. In this figure, the abscess is for the measured fatigue lives obtained from experiments, and the ordinate is for the predicted fatigue lives by the proposed method. The 6 solid diagonal line in this figure signifies a perfect prediction, and the 2 dotted lines represent the factor of 2 boundaries. It can be seen from this figure that the life prediction with a proposed method achieves a good agreement with the experimental data under second loading. Fatigue crack propagation rate is an important parameter to show the resistance of reactive materials to fatigue. Pavier related the stress intensity factor range to crack growth under a fatigue stress regime and proposed Pavier law. The fatigue crack growth rate and SIF range were calculated according to the second method suggested in the ASTM E647. Although the fatigue load used is perpendicular to the preset crack, but the crack will propagate in inclined direction, so 1 and 2 mixed mode fracture will happen in lattice plates. Effective stress intensity factor KEFF is used to study the mixed mode fatigue failure. The SIFs of lattice plates are calculated by using FEM with homogenization methods. The effective elastic properties like Young's modulus and Poisson's ratio of lattice plates can be calculated by formula in literature. The fatigue crack propagation rate of triangular lattice plates in experimental and prediction results are shown in Figure 13. The predicting results agrees very well with the test results. The conclusions for this research are: the method proposed in this report can predict fatigue cycles very well by using the load life curve of single struts to predict the fatigue life of individual struts in lattice materials. The 3-stage pattern of crack length versus number of cycles observed in the test. These lattice plates will break and fail quickly after the failure of struts in second stage. Predictions of the crack paths obtained using this method were also consistent with experiments in lattice of this type develops in a 30-degree to the horizontal axis. The predicted fatigue crack growth rate by proposed method also agrees very well with the test results. So, thank you for your attention. Any questions?